anti-quark, and in this way all these 8 and 10 and various representations can be obtained. So that was sort of the idea. Now this gave new predictions. One of them I'll just highlight for you before moving on. You see, if I have 3 quarks and 3 anti-quarks, then I can altogether make 9 bound states of 1 quark and 1 anti-quark. Just pick one of U, D, S and one of U bar, D bar, S bar and multiply them in all possible ways. Now, SU3 group theory doesn't say that the octet and the singlet have to both occur in nature. It says that things can be singlets or things can be octets. But the quark hypothesis says that all these 9 should exist, but 8 of them should form a group and 1 of them should be isolated. That is the octet and the singlet representation, which you obtain by multiplying these fundamental representations. So the quark model suggests that if you find 8 mesons which all look like combinations of these, there might be a 9th one which has a different mass but is still predicted by the quark model. Sure enough, the eta prime was discovered in 1964, and this is the 9th meson. Look, now, it's not like people fell in line and said, well, all this mathematical stuff works beautifully. That's exactly the opposite of what people did. Both theorists and experimentalists kept asking, if there are quarks, why have we never seen them? In particular, fractional charges should have been detectable from the time of Millikan's famous oil drop experiment, and they were never observed. It turned out we had to wait some time for better experiments, and a series of experiments called deep inelastic scattering revealed that inside protons and neutrons, there are indeed point-like structures, and they indeed have fractional charge, which can be measured even though the quark cannot be kicked out of the proton. Okay, basically, instead of trying to liberate the quark and study it, you fire something which goes inside the proton, interacts with the quarks and comes back out, and its exit and its behavior after it exits tells you what was inside the proton and neutron. And the answer to that question is indisputably, I mean, these experiments were very precise, is indisputably quarks. But even then, physicists were reluctant to call them quarks. Quarks was Gell-Mann's name based on his theory. So Feynman invented a new name. There was some rivalry between him and Gell-Mann. Anyway, they had been collaborators before, but he called them partons. So for a long time, partons were what this experiment saw, and quarks were what Gell-Mann proposed, and quarks were not partons. It took till the 1970s to accept that actually partons that are seen in the experiment are the quarks that Gell-Mann and Zweig predicted. And just for your amusement, and why are they not seen freely propagating? Because of a phenomenon called confinement, which says that they cannot be liberated from the proton or neutron, but one can always go inside the proton and neutron and detect them sitting there. So just for your amusement, here's a conversation. This is extracted from some discussion session in a conference, which used to be, question answer sessions used to be noted like this and put in the proceedings. And Sudarshan asked, could it be that the partons are just like ether? They may never be found. And Feynman says, yes. Maybe it's an irrelevant complication. Maybe partons are also non-existent. They were only put in there, so I haven't got the rest of the quote. But you see, they're trying to theorize that these partons are not the things that Gell-Mann was talking about, and they aren't things at all, even though by this time they had been seen in an experiment. So there's some lessons to be learned about history. Okay, so no questions still in the chat box, but as I emphasized, please feel free to put them there. Let's go to the fourth and last topic of my talk, which is black holes. So, good. So here is a paper that came out in 1916, the year after Einstein published his theory of general theory of relativity. And this paper mathematically found a vacuum solution of Einstein's theory, which has the property that deep inside the solution, there's a singularity of space-time. A place where the laws of physics as we know them break down. And subsequent investigation, well, I'll come to that. So this was the paper. A little historical note, I think Schwarzschild went to fight in a war next year and was killed, and that was that. So he never really enjoyed the fact that 105 years later, well, he didn't even enjoy the fact that 10 or 20 years later, people started to talk about this. But there was a longish gap. It was partly due to the situation in Europe and so on, and partly just because people didn't believe or didn't care. So 23 years later, Oppenheimer and Snyder argued that actual matter could collapse to an object of the kind discussed by Schwarzschild just as a solution to some partial differential equations. And that this collapsed object will have a one-way horizon on its surface so that if anything goes in, that thing cannot then come out. And it's not, as is often said in popular media, that the gravitational field is so strong that things cannot come out. That's also true, but really the nature of space and time changes on the horizon of a black hole, so that once you're inside, even the meaning of coming out is lost. Okay, technically, people say the light cone tips, or whatever you want to call it, and we'll come to that in a minute. But so it took this long to argue just this basic fact that spherically symmetric matter will collapse to such an object. Now, critics always have an objection to everything, and in this case, it was, well, spherically symmetric. Haha, I mean, what is spherically symmetric in life? We are not. Nothing that we know is spherically symmetric. Even the Earth, it has mountains, it has seas. It's not a perfect sphere. So maybe, nothing is a perfect sphere. So maybe nothing does this collapse, Oppenheimer-Snyder type of collapse. Maybe it's just a very idealized fictional kind of situation. Well, maybe it is, but at least people interpreted this as a space-time from which nothing can escape, anything can go in, nothing can come back out. Even light, if it goes in, can't come back out. So the object, unlike a star, doesn't shine. So it's black. And that's why it was named black hole. And these objects were treated throughout my career and that of many of you here who are senior, including for sure Ajit Kembavi. These objects were treated as mathematical curiosities right through the 40s, 50s, 60s. Some work was done in the 60s, I'll be talking about it, but even then in the 70s, 80s, they were still treated somewhat as curiosities. And today, well, okay, let's come to today. Fred Hoyle in the 60s notably proposed that quasars, which were then newly discovered, may be black holes. So, you see that the time gap between something new being said about these objects is pretty large. 10 years, 20 years at a time, they would be somewhat in obscurity. And the problem then was that, nobody, what I just said, nobody knew that generic stars would form black holes. They had to be somewhat special, they had to be spherically symmetric, ideal, and maybe there weren't any such thing. So this problem was revisited in 1964 by a young British mathematician, Roger Penrose. And his first few, so he has a colorful story about him. Let me just tell you a little about him. Of course, people here know him personally, which I don't, but okay. His first paper, I think, was this one, Generalized Inverse for Matrices. Quite a harmless exercise in algebra, trying to generalize the concept of inverse to matrices which formally don't have an inverse, whose determinant is 0. He also, with his father, developed these impossible figures, the impossible triangle and the impossible staircase. For those who are seeing it for the first time, this triangle is a perspective view. If you look only here, it makes sense. This thing is, it's a rod coming up and bending this way. If you look only here, it also makes sense. If you look here, it makes sense. But if you combine them into a triangle, it makes no sense at all. There's no single perspective in which all of these make sense. And therefore, there's really no solid figure you can make which looks like this from all sides. You can always make a solid figure that looks like this from one side, but it isn't what this picture suggests really, because the real thing is impossible. It's called the impossible triangle. A model of it is put up outside the Newton Institute in Cambridge, where I organized a meeting in 2012. But I emphasize that's a model which from the front looks like this. Okay, what about the staircase? Well, in this staircase, if you come this way, according to my cursor, you climb, 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 then you climb, 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 and you keep climbing, and guess what? You're back where you started. Okay, so after climbing 4 ways, you're actually back to the position where you started, which is clearly impossible. So your perspective is being fooled by these figures. Good. In fact, there was a back and forth between Penrose and his father and the Dutch artist Escher, who famously drew that impossible staircase into a painting, which is very popular now, where soldiers or whatever they might be are walking. One set are walking uphill. So one set are walking uphill, and reaching the same point. The other set are walking downhill, and coming back to the same point. So people love these pictures. I used to love them myself when I was very popular with college students. Okay, very nice. But all said and done, these are cute mathematical ideas. But in 1965, Roger Penrose published a paper studying in detail the time development of collapsing objects as predicted by Einstein's equations and later studied by Oppenheimer and Snyder. And this is a very, very famous diagram from Penrose's paper. So it looks like a weird rocket ship, but it's not. You're supposed to think of the vertical axis as time. So, the circle here is a star. It's just represented as a circle. It's really a sphere. As time progresses, the circle is shrinking. So the star is collapsing under the weight of the matter that it has. And what Penrose showed was that under suitable initial conditions, which are fairly general, a closed trapped surface can form. That is this one here. And it has the property that once it forms, even though a black hole hasn't yet formed, collapse is now inevitable. So there's a situation where a collapsing object is now destined to continue collapsing and form a black hole. Okay, and now the interesting thing about this paper is that it was all of 3 pages long, and that I would estimate 99% of physicists, if you include physicists working in all branches of physics, would not be able to follow this paper. I've looked at it a few times. I think I can unravel it, but I struggle, and I have a training in general relativity, but it's a tough act to follow. But the conclusion was very simple. After a certain time in the collapse of a star, even deviations from spherical symmetry cannot prevent this collapse and cannot prevent space-time singularities from arising. And therefore, a variety of stars, not just an ideal star, will collapse into black holes and will have this peculiar singularity property at their core as well as a horizon. He noted that the horizon and the singularity seem to go hand in hand. Somehow laws of physics are breaking down deep inside the object, but luckily, so to say, the surface of the object is covered by a one-way horizon, so that, let's say, a person goes in and is exposed to this broken down laws of physics by the singularity, at least that person can't come out and spill that knowledge in our sensible universe. So this is called cosmic censorship, the idea that objects which form in cosmological evolution may have singular behavior inside them, but we can't know about it. Okay. Today's view of it is a little more sophisticated, but it's still interesting. It's still an interesting observation. And in fact, in 1970, Hawking and Penrose joined together to give a general theory of singularities that would apply both for collapsing objects and for cosmological evolution. Good. Now, 50 to 55 years after Penrose's work, black holes have gone from being a mathematical curiosity, which is what most people thought, and certainly when I did my PhD, that was a prevailing view. Even now, I would say that if you ask an average physicist, they probably think it's still a mathematical curiosity unless they read newspapers. Physicists don't read newspapers in general, but if they did, they would know that these are the most common objects in the universe. They are estimated to be at least 100 billion supermassive black holes in the universe, each with a mass of 1 million to 1 billion times the solar mass. But there are also others which are not supermassive, which are stellar, intermediate mass. They might even be small mass black holes, for all we know. And LIGO has observed their mergers very, very unambiguously. In fact, the Nobel Prize went to the person who understood this collapse process, and the two people, Ghez and Gensel, who played a key role in discovering one particular supermassive black hole. And note that Penrose got half the prize, the others got a quarter each. That's done in the Nobel Prize when it's not just greater and less than. It's in some sense Penrose got that half of the prize reserved for the theoretical prediction of collapse being generic, and the other two got it for that part which is for the experimental observational detection. So this is how it was shared. Okay, so that completes my history, and I think I have 5 minutes. So in those 5 minutes, I'll share some thoughts, but maybe I can answer one of the questions. There is one. Can we construct these imaginary structures? Well, the whole point is that it's impossible. There cannot be an object which from all angles looks like this structure, this triangle that I showed you. So it's called the impossible triangle. It shows that you can draw something, therefore you can imagine it, but you, in the process of imagining it, you realize that it cannot be actually true, because if you see the light and shade effect on that figure, it would require different light and shade effects on the three parts of the figure, which don't fit together at all. So that's just a fact. You can make something, as I said already, you can make something which from the front view looks like that. And that's been made, and it's sitting there in Cambridge in front of the Newton Institute. Okay, so here are some thoughts. My thoughts, I mean, they're not very deep, but just some comments. Physics is not just a directory of objects and behaviors, but an organized and very universal structure. The fundamental interactions are only for electromagnetism, weak, strong interactions, and gravity. And as far as we know, they're the same in all parts of the universe, and they're described by very sophisticated mathematical formulas. Wigner marveled at the fact that mathematical thinking plays a sovereign role in physics. And my feeling, which I think is shared by many people, is that there's something called universal laws of physics, which is like a universal way of formulating the theory of physics, of which standard model of particle physics is an example, general relativity is another example, and both are special and maybe approximate cases. The bigger laws must be based on some as yet unknown symmetry principles, because we've seen that symmetry as embodied in the group theory was an important aspect of how these special theories, particular theories, were thought of. The universal laws can be called unified theory or final theory or string theory, but we're not sure, so it's better to just call them universal laws. And Steven Weinberg, who passed away literally 2 days ago, and is very sad, of course, he did live a full life, wrote this amazing book called Dreams of a Final Theory, in which he lays out the search for these so-called ultimate laws of nature. And I would like to emphasize that the search is still alive. I don't think Weinberg highlighted so much in his book a fact that we are now beginning to understand, that these are not just ultimate laws of nature, they are ultimate laws of physics. So they could apply not just at the basic level of elementary particles, but maybe in matter, in materials like topological insulators. Okay, in complicated systems, complex systems, which have a whole new set of physical principles organizing them, that of putting together millions of atoms to form some kind of collective behavior. Even then, these laws can apply. And it seems rather that nature's template for reality is based on these laws and phrased in the language of mathematics. I think this is a reasonably non-controversial statement. Now, here's something I could have talked about, and actually in some version of this talk it was there, but the talk became too long. You see, there's something called the Higgs mechanism, which led to the Higgs particle. There's also something called the Anderson mechanism. The Anderson mechanism and the Higgs mechanism are the same mechanism, but Anderson proposed it in the context of condensed matter physics, and Higgs proposed it in the context of particle physics. Out of these two, Anderson proposed it first. Something that is not very well known is that Anderson proposed it as a condensed matter analogy for something that might work in particle physics to describe weak interactions, exactly where Higgs implemented it. Higgs didn't cite Anderson's work. Maybe he didn't know about it. Anderson didn't cite Higgs's work because it hadn't yet been done. So you see that nature is doing something and human beings find a little bit this and a little bit that depending on the specialization where they work. And it turns out that they are exactly the same. So now people use Anderson-Higgs or Higgs-Anderson mechanism equivalently when talking about the general phenomenon. Sometimes the phenomenon doesn't hold in two branches of physics, but only one. But it's not the one that people thought of, like Majorana fermions and axions. It may be true that they exist in vacuum and in materials, or they only exist in materials and not in the realm of fundamental particles. We just don't know. So this perspective says that research on the universal laws can be more effective in the long run than research targeted on a specific physics problem. And this is not to say that research should not be targeted, but that people who do targeted research or who sponsor or support targeted research should not forget that research on the universal laws sometimes has a role which overwhelms all the targeted research of its time. And no example is better than that of Wilhelm von Röntgen, who discovered X-rays and did more for medicine than the medical researchers trying to solve the problem of bullets embedded in the bodies of soldiers at that time. And since this is Pune Knowledge Cluster, I really want to share this with you. This is a picture of von Röntgen in the waiting room of KEM Hospital in Pune, which thoughtfully has put a garland on him. And if this talk doesn't inspire you to do anything else, it might inspire you to think that these are the kind of people for whom garlands should be ideally reserved. So yeah, I felt very proud of Pune, though I'm not been here more than 9 years, but I really felt great when I saw it. Okay, very good. Now there are some more comments, but I think I would like to skip them because in the interest of time, it's already an hour. So I would conclude that the mathematical approach to physical reality has worked. It undergoes a lot of obstacles. It is maybe rare, but in the long run, everyone must accept that it works when it works. So I'll close with a quote from this person who obviously has to feature in any such talk. He says, pure mathematics is in its way the poetry of logical ideas. And somehow what binds pure mathematics to physics, I think, is that both of them intimately involve this poetry of logical ideas implemented in the way that nature had in mind. So that with that quote, which by the way I had not heard before today, I will stop and take questions. So I see there are some questions.
Thank you so much, sir. It was indeed an inspiring talk, and to see the journey of science, especially the scientists contributing in these areas and so on. So thank you so much. We have a question. So what kind of nature the wave functions of hypothetical particles have, and how they are different from real particles mathematically? Is the question.
Thank you. It's a good question. So they are not different from real particles mathematically. So the mathematical description of an axion or a dion is basically the same as the mathematical description of an electron or a quark or a neutrino, but with some small modifications. The broad picture of it is the same. For example, if you put a dion, if you put it in an electric and magnetic field, it will respond to that field exactly the way Maxwell's equations modified to accommodate magnetic charge would predict. So they're not that exotic from that point of view. The problem is, we could just think about dions as something that's fun to think of, but Witten had a different take on it. He said, look, dions must exist if monopoles exist in any theory which violates Cp. And if you ask him today, probably he'll say, that's what I said. So if monopoles don't exist, or if Cp violation isn't true, then dions probably don't exist. But mathematically, there's no difficulty to discuss them once you understand the little subtlety. It's a very beautiful and important one, which came out of his famous and very short paper in the 1970s. So yeah, so they don't differ in that way mathematically. Is there any way to know the entropy of the interior of the black hole? Well, that's a whole, from the same person, that's a whole separate talk on entropy of black holes. It's a very interesting subject. I can't do any justice to it in a minute, so I'll skip that. That's a whole other discussion. It's very much within the framework that I have laid out here. I don't see any more questions, but if anyone...
We have a lot of comments from people that it was an excellent session.
Thank you so much.
So I had a question, sir.
Yes.
Maybe it is a basic question. So as we know that, Higgs boson is the celebrated particle and so on. Does Higgs boson have an antiparticle? And if it is, what is the role of, that antiparticle?
Yeah, thank you. So actually, it's an interesting fact that, particles are not obliged to have an antiparticle as long as they are neutral. If they have an electric charge, they must have an antiparticle which has the opposite charge. This is a general rule. It's called the Cpt Theorem, and it's a rule of quantum field theory. Now, how many particles in nature do not have electric charge? Not so many. I can list them for you. The photon. And so therefore, photon, in fact, doesn't have an antiparticle. The antiparticle of photon is itself. The Higgs possibility that there may be other Higgs particles which do have, those would have to have antiparticles. But the one that was found, yeah. Can you hear me? There's something saying my connection is unstable. Yeah.
We can hear you, sir.
The known Higgs particle does not have an antiparticle because it's neutral.
Yeah.
Okay. Neutrino.
Maybe also. Yes. No, sir, you go ahead.
Yeah. Neutrinos are also electrically neutral. In this case, it's a bit more complicated. We know that at least some neutrinos have antiparticles different from themselves. We know this from experiments. But some neutrinos might actually be Majorana fermions, and in that case, they would fulfill Majorana's exact prediction that there are particles in nature which satisfy the Majorana equation, which is a slight variation on the Dirac equation.
Thank you. Thank you so much. So if any of the participants have questions, you can type it in the chat box. I can't see any questions. Okay. Thank you so much, sir. It was a wonderful talk.
Thank you. Thank you.
Sir, would you like to say?
Yeah.
No, I would just say thank you, Sunil, for even a biologist like me would not got interested in all this. So very nice. Thank you so much for accepting our invitation and doing very sincere justice to your topic. You actually wanted some more time, I think, but
no, I think this is fine. So much can only come.
Sunil, what you could do is to give a short course on this kind of a theme for us, which will gather a lot of people. Because we have a number of courses going on in various subjects. And so maybe a 4-lecture thing or something, or even longer one if you like.
Can be done. Unfortunately, I'll be teaching 2 courses at ISA in the coming semester. But eventually, I mean, I think I shall be freed from the employment of Government of India finally in a year from now. So that would be an ideal time to think about these things.
Yeah, but we would very much appreciate a shorter time scale.
Okay, then let's try to find a suitable time.
Okay.
Perhaps on some Saturdays, it need not be continuous. You could have maybe once a week or something.
All right.
Okay.
Can be done. Definitely can be done.
So Prachi and Shilpa.
Yes, sir. Yeah. That would be really interesting to have a course on this.
Thank you. Okay. Thank you so much. Thank you. And thank you for our audience. Thanks to the audience for all the nice comments. Yeah.
Thank you.
So.
Yeah. Thank you, sir.